Okay, thank you. The first thing I would say is if you want, come over here, because I'll be drawing things here. And you may want to come closer, so feel free. Okay, well, he already introduced me. My name is Álvaro. Sorry que no falo portugués. But I can understand quite well. So if you want to ask in Portuguese, I will try to understand. If not, someone will help me. Cool. So, Sebas, where are you? Well, he's guilty for many things, obviously. I hope he's... Do you hear me? I'm saying you're guilty for many things, obviously. Yes. Yeah? But especially for one. He told me no slides. So you and me will suffer tonight going without slides. So I'll draw maybe some stupid things here. Just before that, a little bit of introduction about myself. I've been working with databases and specifically with Postgres since probably, if I'm not mistaken, 1997. That's a long time, yeah. As of today, I run a company. I founded a company, a startup focused on Postgres called OnGres. It's the shorthand for on Postgres, so it's pretty obvious what we do, right? I also like to speak at events like this one. Lately coming a lot actually to events here in Brazil. I'm trying to help, or I get invites, a lot of invites to come. In particular, I try to also get slides, except of today, and recordings of my talks. And if you're interested, and also if you want to learn a little bit about my biography, I collect everything. Sorry, you cannot see me now, but I'll be super fast here. I collect, no, sorry. That's not what I wanted. Doesn't matter. It's only about Real Madrid stuff. I collect a personal website, aht.es. AHT are my initials, and ES is Spain. So it's pretty easy, aht.es. I collect all my talks there if you're interested. And right now there's, more than 140 talks there. Mostly about Postgres and databases, but also there's stuff about cloud and programming. So if you're interested, feel free to check this out. All right, so let's start drawing, or almost. So what I want to talk today about is sharding. So first things first, who doesn't know what is sharding? Okay, it's good because I need to find, okay, thank you. Now I see a lot of people lying. No, I'm kidding. Cool, so we're gonna dive a little bit into sharding and some of the ideas, right? Sharding starts from the concept of scaling, right? I want to accomplish more with a database. I'll be talking obviously about Postgres, but this is a general concept most of the time. So let's talk about servers. Let's say I have a server here, right? That is providing queries, it's serving queries, right? It's writing data, reading data. And let's say that is doing right now, doesn't matter the number, like 1,000 TPS, right? Well, not KTPS, 1,000 TPS, right? Or, I don't know, 1,000 TPS. And let's say it's running an average at this capacity, let's call this 70% usage of resources, CPU, RAM, whatever, right? So this is our server. And manager comes and we expect our load to grow in the next few days, months, and we need to scale. This is the magic word, scale. So what do we do? Ideas? Go up, more hardware. Go up, okay, I like this idea. So I didn't mention how many cores or RAM this have. It doesn't really matter. I can make my server bigger. This is what you meant, right? Cool. I agree with this because now this, I should probably delete this part, and now this is not 70% anymore, this is 40%. Which is very good, because now I can grow my workload probably up to 2.5 times more. Right? Ideally less than 2.5, so I don't want to run always close to saturation, so maybe 40%, 2 times more, whatever, right? Okay, but manager comes and say, no, 2 times more. Our service is gonna be Google size, right? We're gonna grow like crazy. We're gonna be the next Amazon, the next Citus, whatever, right? So what do? We need to scale more. But let's go step by step. Don't go full blown yet. But what can we do? what would you do typically with a database? Okay, thank you very much. I like this idea also. So instead of having one server, let's add another server. We have two servers. Now, this server is a bit special because this one, in most database architectures, this is called a primary, and this is called a replica. The replica only handles read queries. Right? There's other database topology where this is not exactly true, but this is the most common case, so I'm going to focus on this one. So from the primary to the replica, there's typically a continuous network stream replicating, hence the name, the changes that happen here so that both servers have the same data, or almost the same data. Could be eventually. Could be totally consistent or eventually consistent. We're not getting into this now. But it will have part of the data, which means that instead of this 10,000 TPS, which now could be up to 2.5, let's say this can do 2.5 KTPS, now I can offload part of the queries here, let's say 1.5 KTPS plus the capacity, so maybe it will grow. I mean, it will be able to do another 2.5, right? That's the capacity of the server. But they're only read-only, but it's okay. Now I split my workload between read-write queries and read-only queries, and I can grow more. So now I can do 5. So I can grow like 4 times, right? More or less. Napkin, back on napkin math. Whew, not bad. What else can we do? We need to scale more.
Can add another primary and divide the writes for different customers in different databases, in different instances.
Okay, that is sharding. So that it's absolutely correct. I'll just keep it for a little bit later, okay? We still need to scale without going into that. We are going into that today. That's the purpose of today's session, right? But before getting into that, what else can we do?
More replicas.
More replicas? Yeah, easy. Instead of one, we can add more. I can still only scale the read-only queries, but actually normally read-only queries are most of the fraction of the queries. So this is not a bad pattern. What else can we do? Cache. Yes, this is a very interesting topic. I'm going to leave it aside. Who said cache right away? That's a great answer. It's just a totally different topic. I don't want to touch on today. Yeah, it's probably very useful, and there are some applications which cannot live without a cache in front. But I want to still scale the database by itself. Well, it's a bit of a tricky question. I just want to reinforce that vertical scaling is a super powerful mechanism. I cannot paint above this, but really you can go up. I'm not super tall, but I hope you get the point. With vertical scaling, today, you can achieve a huge amount of scalability. Again, they don't have the space, but right now there are servers on cloud infrastructure that you can get with hundreds of cores, a few terabytes of RAM. And on these machines, you can run in the order of 1 million transactions per second, per server, right? Plus replicas, you could be running a cluster that does a few million transactions per second. How many people do millions of transactions per second? Very little. Definitely less than 1% of the services in the world. Yeah, so there are cases, but it's probably, I don't have the numbers, but it's probably like 0.1% or even less. So do I recommend, so vertical scaling can go so far, plus adding replicas, as you all well said, that with this architecture we can get very, very, very far. And if we can get this very, 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 very far with this, do it. Now I'm going to talk about sharding, which is like, okay, let's do something else to scale even more. But sharding comes with, like anything in technology, with caveats, right? And before jumping into, oh, let's sharding because this is what I read on Reddit, that is the next big thing, and we're going to scale Google size. Well, because not everybody reaches Google size, and because it comes with caveats, maybe you don't want to do sharding, or not yet. And you can do very well with vertical scaling. Now, I'm going to flip over this, and I'm going to argue for exactly the opposite, that you should do sharding earlier. So, let's think about this. What is the main reason for sharding? It's kind of already stated. Increase the performance, right? You are proposing sharding. What do you think is the main reason for proposing a sharded architecture? I/O capacity is going to come for sure with sharding. It's kind of a consequence. What I'm meaning by the main reason is, why do we think of sharding? We think of sharding because we want to have more writes, essentially. Here on this architecture, we can scale reads easily. If our application supports this pattern, right? I can divide writes and reads. But the writes, I can scale vertically, and I said just before, you can go very far. But at some point, you hit a limit. Just a quick note, I just came across a thought. 15 years ago, I went to a presentation about one of the latest Sun Microsystems rack. And it was an incredible machine where you can swap out CPUs while in production, 15 years ago. And I remember it had 144 processors. No, it was not 144, that's a good number. It was like, I don't know, like 121 processors. It's like, that's a really odd number. And I went to the presenter and asked, like, why this strange number of CPUs in the rack? He said, our customers request these racks fast. We need to ship them by plane. This is the amount of processors we can put on a cabinet that feeds it through the door of a plane, of a cargo plane. Why I'm bringing this? Because there is, at the end of the day, a limit to vertical scalability. At some point, you cannot add more CPU processors, right? Because that computer needs to go to some cloud provider, and that needs to go through a plane, and there's a limit, or it doesn't matter how it says, but there's a limit. So, sharding. Sometimes it's also called horizontal scalability. The idea before sharding, and I will explain what is sharding, but the main goal is to increase the writes. Add more write capacity. So that when I hit this limit, or when I think I'm going to hit this limit, I can still push more writes. Otherwise, by the previous architecture, I'm very limited. But coming back again to what I was saying, if this limit exists, obviously, but it's very high, I can do 1 million write transactions per second on a beefy server, who cares? Only those who will reach this, but this will be 1 or 2 of you here, and the rest can go already drink beers and forget about me. Or not. So who can think about, why may I do sharding before I hit or even estimate that I will hit the limit on writes?
Well, it's a bit more tricky, but regarding reliability, blast radius, sharding can help there. However, you've got to be careful, as always, with reliability.
I subscribe your words one by one. Blast radius. What is this? So, in sharding, we're going to split our data, and I'll explain how this works, into multiple servers. Each server is going to contain a subset of the data. Let's assume I have this architecture. If this cluster fails, for whatever reason, yes, it's going to be highly available, it's going to have mechanisms. If this server dies, it's going to be promoted, it has replication, has backups, blah, blah, blah. But if one day, someone goes and say, stop HA component, stop cluster, the cluster is going to go down, right? If some update of some component, this happens from time to time. And then you incur in a downtime of 2 hours. The on-call service gets called, PhD, blah, 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 try to find out what happened, and it gets restored in 2 hours. Some companies cannot tolerate this. If you're an e-commerce, right, and you're down for 2 hours, you know how much money do you lose. Sometimes it's a lot of money. But you also lose in terms of PR, marketing. people will complain, oh, this site is down. This is a very bad image for the company. Someone will not buy again because this site doesn't work. So blast radius means that if I have an explosion, and explosions sometimes happen, I need to make them smaller so that whatever they destroy is smaller. If I have my data split into multiple clusters, they're independent, as we shall see now, and one fails, okay, 10% of my site is down, which means in reality 10% of my users are down. They will complain. I'll be transparent. They'll say, yes, we have a problem. But most people will say, no, it works for me. It works for me. It works for me. The PR impact is minimal. And most people still get service. My losses are 10% and not 100%. So thank you for that. These are the two main reasons for sharding. So I said before, go vertical scalability as much as you can. Yes, as long as you can control your blast radius. If you can tolerate being down for a couple of hours and nothing really serious happen, go vertical scalability. If you cannot tolerate this, then go reduce your blast radius. All right. So how does sharding work? The idea is that, let's say, here's my non-sharded database, right? And here I have my data. I'm gonna draw some subset of data, right? This is all my data. What I'm gonna do with sharding is create more clusters. For example, I can create 4 clusters, 4 servers for now. We'll talk about clusters later. And I will say, you have only this set of the data, you have only this, you have only this, and you have only this. So they each become essentially smaller. Could be the same size, but I mean, the data is split. And I will write here independently of here, independently of here, independently of here. So if this server has whatever amount of resources, and this have, for example, the same, now my I/O capacity, my capacity to do writes is multiplied by 4 instantly. And the blast radius gets reduced because if this guy dies, the rest keep working. Any question up to here?
But you have to add some complexity to each of these boxes, right?
Absolutely.
To gain reliability on each of these.
So there's 2 topics. I need to do many more things with this, right? I need to add high availability to each of these components. And I need to add something that kind of brings my database back together as a single unit, logical entity. Well, I'm going to talk about all this. First of all, I'm starting to explain how the concept works, right? More questions?
How do you join the data?
OK, I'll get into that. Sorry not to answer immediately, but yes, I'll get into this.
Another thing that you use scale is the reads, right? If you can,
Of course.
you can read all together.
The same. OK, so let's go a little bit into how do I split the data. So this is one of the caveats of sharding. There's no good answer. And it really depends on your use case. So it's hard to find out like a general answer for this. But most of the time, you try to split into subsets of data which are mostly disjoint. OK? This sounds very abstract. Let's use an example. So if you're a SaaS application, and the data you're storing in your database is what you're buying, your shopping cart. Normally, shopping carts are independent. What you buy is different from what you buy. You don't want to know what he buys. You don't want to know, well, maybe you want, but not at the database level, right? That's my point. So they're disjoint. Your data is disjoint from your data. So then we can separate and put into different groups. How do we do this? For example, let's do a simple example. This is not production quality, but let's say in the database, there is the customer user, the customer name. So let's pick the first letter of the name and split it. So there's 26 letters in the alphabet. Let's split into 4 groups, to 3 to make it simpler. Let's go maybe almost like 9 letters per group. So A to J letters, yeah, this died. Let's forget about it. So customers whose name starts from any letter containing this range will have their data here. If they start on K to S, it will go to this server, and T to Z will come to this server. So far, so good. So this is essentially how sharding works. The way I decide by which criteria I'm going to split the data, this is called the sharding key or the sharding criteria. And it's key. Whenever I'm going to do sharding, the first thing I need to think is, what is my sharding criteria? If it's a poor one, it will significantly diminish your scalability. Let's put possibly a terrible example, but let's say our sharding criteria is not these letters, our sharding criteria is gender in this room. Okay? There might be 2 or a few more genders, servers, right? But most people I see here are going to probably, I don't know, declare their gender as male, right? That means that the male server is going to be fully collapsed of data and activity, where the others, in this particular case again, will be with much less load. So our scalability is totally limited by this server. So you need to find a sharding criteria that tries more or less to do a uniform distribution of the data. Again, on an application where there's millions of users or a huge number of users, and they're independent of each other, that's typically called a multi-tenant environment. And then it's very easy to shard by tenant. Tenant could be the tenant ID, the email, something like this. Okay, so we know more or less how to distribute data. And we can talk a lot about sharding keys, sharding criteria. I'm not going to get into all those much details. I want to focus a little bit more on the architecture part today. So, okay, we have this. I'm going to use 3 because I'm lazy painting today. The 3 servers. Each one will have their own subset of the data. Of course, they can increase this data. Let's paint it like this. Now, one of the questions, your question actually, is, okay, how do I see this? How do I join the data, or how I see this? Now I don't have a database. I have 3. So how do I query this? Do I need, me as the application, do I need to say, hey, is my data here? Is my data here? Is my data here? Well, actually, no. There's 2 options of doing this. One is what I call application-assisted sharding. The application understands this sharding criteria, this sharding logic, and then can compute the same algorithm and know where the server is, the data is. So if we're picking the first letter of the customer name, the application can know this and then decide which server to query. This is okay, but if the sharding logic evolves, gets complex, you need to reproduce into every application that connects to the database, it might be burdensome for the application. Sometimes it's better to opt for transparent sharding. Transparent sharding means the application doesn't need to know. So how does transparent sharding works? Well, we set up another component here, which we typically call a coordinator, that implements this logic. This guy understands.
It's a custom application or a postgres component?
It's a really good question. It depends. There are cases for both. So this coordinator, first, conceptually, is someone who understands this topology, this sharding criteria, and will know how to route the queries, right? PG Bouncer in particular will only do connection pooling. Let me give a couple of examples, right? Just to complete the picture first, so the application, which I'm going to represent by a database client, will connect to this coordinator, and this coordinator will know how to query the data. So this guy, the application, doesn't need to care about sharding at all. That's why it's called transparent. So there's 2 types that I've seen. In Postgres world, this can be a Postgres server by itself, with 2 different technologies that I'm going to explain a bit later, okay? But there's other technologies that are an independent piece of software that run this service, this sharding criteria, and work equally well. Sometimes this is called a proxy, because technically it's a proxy anyway. It implements a protocol for the database, impersonates the database, and performs this function.
Or at least a query router, right?
Huh?
Or at least a query router.
Yeah, sometimes called query router also.
Yeah, but it's much more complex than that. You need a distributed query plan, you need a distributed query executor. It's more complex than just a query group.
Yeah. There's 2 types of function that this coordinator needs to do. One is route, right? querying about customer whose letter starts by M, it should write to here, gather the response, and bring it back to you. But sometimes you want to join data. I said, I want the total count of shopping carts orders created today. That query needs to go through all of them. And this piece of software is or should be capable of dividing this query into 3, let's say. Exactly. Gathering the data, merging it in memory, and returning it back to you. That's why this piece of software ends up being complex by itself. That's why either there's occasions where this is an independent piece of software, sometimes it's Postgres with some tricks that can be employed, and because Postgres already understands how to aggregate data, how to split data, etc. I'm going to mention all these cases, right? So this is the role of the coordinator. Let me focus a little bit more on the architectural part. So now we are able to scale horizontally, to split the data, blah, blah, blah. This is good. Reduce the blast radius. Are we in good shape? Let's go into production. We have a good sharding key, good sharding criteria. Are we ready to go to production? You already hinted that no. But why? What's wrong with this architecture? What's left? You said it before.
The redundance for each of the parts of the shard.
Exactly. So what happens is if this server, this guy dies, I only lose 1/3 of the capacity, but I still don't want to do this in general, right? So I want to have high availability for this component so that it fails only if something really serious happens. So most of the time, my architecture is going to look like more like this. I'll have the coordinator, and then I'll have the shard, let's say shard 1. This is going to be primary. Look how my boxes look like. I'm terrible drawing, sorry. This is the shard 2. This is the shard 3. They're all. And then I'll have 1 or more replicas here, right? Shard 1, replica. You get the point, right? Now, if this guy fails, this one will take over, and this part of subset of the data will only fail if this whole thing fails. Does it make sense? Excellent question. Excellent question. We're not ready yet because coordinator is still a single point of failure. So I also need to make this redundant. I can do actually the same. I can do a primary, and I can do a primary, and I can do a replica. Now, this starts to be interesting because if you think about this, now we need to configure connections to here, to here, to here, to here, to here, to here, 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 here. What about the application? How now the application connects to the database? The database is the coordinator, obviously, right? So there's 2 options. One option is I will always connect to the primary because I don't need to scale. Potentially, sometimes I may need to scale the coordinator itself, even though it doesn't have data. That's all in memory, and CPU normally is not doing a lot of work, so most of the time I don't need to scale this. It's okay to connect to one. If this one dies, I connect to the other one, for example, via virtual IP. But sometimes I really need to balance across them, and in this case, I will use something called a load balancer, hardware or software or whatever, and my application will connect to the load balancer that will balance the workload across the coordinators. These coordinators can be stateless, right? So it doesn't matter which one is being picked. Huh?
Do we need to scale the load balance? Now it's a single point of failure.
Yes. But I'm going to leave this as an exercise for the reader, in this case for you attendees, because it's very well known in the industry how to solve this problem of scaling the load balancer. Cool. So easy, right? Expensive. Yes. Yes, it gets expensive. But
It more expensive than the physical load, right?
it depends. It depends. It's a good question. The advantage of this scheme, actually, you also mentioned, is very important. You can scale I/O much faster than CPU capacity. CPU, if you have here 10 cores, 10 cores, 10 cores, and the other one you have 30, is the same. But I/O will not be the same. If there's an SSD, SSD, you have 3 SSDs now. So I/O is much easier to scale. Sure, you're going to pay more. But if you need this, now, my main point is, okay, who wants to go tonight and build a sharded cluster? You can do this with Postgres, for example. So, okay, go and do it. But do it fully automated, like Ansible or something, right? Because are you going to repeat all this? Oh, and by the way, not 3 shards, make 10. That's more usual in production, right? Something like this, or 12, or 16. 200. You can do 200. So, can you do it tonight? Probably not. Okay. So the demo, I don't know how we're doing with time. How are we doing with time?
No clue.
I have no idea.
How much time?
It's 20 past 9.
How much time do you need?
I don't know, 15 minutes.
Okay, good.
Okay. So I will show you at the end of the session a super quick demo on how I can build all this fully automated with connection pooling included, with everything essentially you need for production ready in exactly 20 lines of tiny YAML and 5 minutes of execution time.
For free.
Yes, fully open source. Sounds good? All right. So before going to that, let's talk about different sharding technologies. Mostly focused on Postgres, sorry. Sharding technologies. The first one, Citus. Citus is an extension to Postgres, for Postgres. Postgres has this concept of extensions. They're like plugins for the browser, pieces of code that you can add to the database, and they add capabilities to the database. In this case, this extension is so huge that it turns Postgres into a sharded database. No less, no more. The architecture is, okay, I'm going to paint it again, but there's a coordinator. There are shards, they call them workers, so I'm going to use their terminology. Every node here, and of course the coordinator can be, etc., etc. There can be replicas. I'm just going to avoid all this part to repeat. The cool thing about this is that all servers here are Postgres, including the coordinator you were asking before. So the coordinator is a Postgres server with Citus extension. Every worker is a Postgres server with Citus extension. That's all that you need. In reality, Citus is actually quite powerful, so much that you can even deploy without coordinators. Each worker is a coordinator on itself. But this has drawbacks. So if you query this one and data is on this one, it will need to be routed. But that's okay. If you're not sure where to connect to, you can connect to any node and it still works. So Citus is a very good option, very interesting option. And again, this coordinator, it's a Postgres server with just the extension. There's another technique that unfortunately doesn't have a name yet. It's kind of homegrown. We lately, well, I'm going to call it FDW, plus partition. Yeah. So Postgres has another technique called a foreign data wrapper. Foreign data wrapper, FDW, is a technique that simulates a table inside of Postgres database where the data is stored outside of Postgres. It can be many things. It's an API, and you can have many implementations of this API. It can be a file. It can be an Excel spreadsheet. It can be a CSV file. It can be remote. It can be another database, like an Oracle database, a MongoDB database. It can be IMAP protocol, so you can read your emails with doing SQL queries. Okay. And it can be another Postgres database. So via this technique, I can represent a Postgres table as a local table that in reality is present on a remote server. Oh, this looks like a lot of what I want to do. So I can build, I'm going to switch pages for explaining this one. I can build a coordinator. Shards are easy, right? Like you get a shard here. And how I build this coordinator with this technology of foreign data wrappers? Well, let's imagine I have my table here. It's inside of the shard table, right? And here I want to have these 3 tables represented. My boxes are even worse. No? So this should point here, this should point here, this should point here. And I can do this via this FDW. So here, first I need to create what is called a server. FDW server. So I create here one server points here, another one points here, and then I create a virtual table. This virtual table points here, this virtual table points here, this virtual table points here. Point.
The shard members are unaware of the partitions?
Yes. By the way, so far there's no partitions here. I call the table 50WM partition. I'm going to get there also. So far it's table mapped, table mapped, table mapped. The cool thing about this is that these virtual tables here, they behave like regular tables. So I can call them partitions of a parent table, or top-level table, which is a partition of these smaller tables, which are remote. Now, if I query the parent table, Postgres will do the right thing. Meaning, if the data by the partitioning key, you determine that the data can be found on only one table.
But you have an index performance panel? How the index will behave in a structure like that?
Yeah. So
Because Postgres will more or less push down the scans to the nodes. Because you scan a table on the coordinator node, and actually you are not scanning a local table, you are scanning a remote table through an API.
But you have to scan all the partitions?
No, the partition is one strategy that we have plenty of organizations to partition by range, like
query for each.
and then I scan just one partition, and then this partition is remote. Then I go to the remote server, push down some predicates, get the data out through the network, and send out.
it really depends on the query. But the way you should design this is that when you create partitions, you need to specify the partition constraint, which is the predicate that makes the subsets disjoint. If you make this partitioning constraint exactly the same as your sharding constraint, and you make a query including a where clause that includes that same constraint, like, and the first letter of the customer username equals C, then the planner picks the right partition, and each partition here happens to be a remote server. But if you do a query like select count star, it's going to go to the, but at least this Postgres knows how to aggregate results across partitions. Okay? So that's how it works. Now, let me dive in just 5 minutes a little bit to try to get you upset about complexity here. But we have 3 shards here. What if tomorrow we need a 4th shard? Okay, we add it. Yeah, but now it's empty. Which data do we put here? Oh. Shall we chop off part of here? No, because there's a partitioning key, sharding criteria, right? So most of the time, you don't do this either. Most of the time, what you do is what I call virtual shards. Woohoo! Let's virtualize everything. So on my servers, on my shards, on my workers, what I will do is I will create a partition table, right? So I'll have a parent table here, and then I have multiple partitions, and the same in all of them. And in my coordinator, which is has a lot of things. So these are partitions of this table, right? And here, I create these partitions, and they're, oh, well, I'm inverting the colors. Sorry. This is a parent table of these partitions. Actually, I have only 3 of these. And each of these points to the parent table on each worker. Now, other than making it much more complex, what have I gained? I have gained that if tomorrow I need to add a 4th server, what I can do, here we have 4, right? So let's paint this 4. Can be anywhere, doesn't matter. I can say, okay, I'm going to move. And this is a complex operation, but not so, I just need to physically move data. I will move this one here, this one here, this one here, and, well, now this has 3, this has 3, this has 3, this has 3, perfect rebalancing. Now I've added a fourth node. So this combination of partitioning at this level with virtual servers and at this level is what I call this 4 in the wrapper plus partitioning. Normally you pick a number of partitions quite high here. Actually, there's one blog post at Uber, I think, that determined a good number, which was 160 or something like this. I don't remember exactly, but it's basically a number that is divisible by many other numbers. So that for many combinations of adding nodes, you can always redistribute these virtual shards easily. Right? You don't need to create uneven workloads. So, okay, now go and program all this. Create all these virtual shards. For doing this, by the way, typically you create the way the data is physically distributed. So, yeah, because you don't go by the letter of the name. You typically use a hash function, which produces a long value. And then we take this long value and map over the ranges of the minimum value of a long and the maximum value of a long divided by the number of virtual shards. So you're creating partitions that go from minus blah, 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 blah to minus blah, 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 blah. The next one from minus blah, blah, blah plus 1 to whatever. And this is a little bit of complicated math. So again, go and do this tonight. You'll finish next month. There is the last one, and this is the last thing before the demo and maybe some questions. Third technique for partitioning, which is, or a technology that I wanted to highlight, which is called Sharding Sphere. And Sharding Sphere, it's an Apache project, independent of Postgres, that supports actually both Postgres and MySQL, has a very, very similar architecture. The workers, the coordinator. The main difference here is that this coordinator, and I'm coming back again to your question, is not Postgres anymore. It's a different piece of software built from scratch. In this case, it's programmed in Java. And implements all the magic to talk to the workers nodes, which can be Postgres or MySQL. Actually, they can be technically mixed. There can be 2 Postgres and 1 MySQL. Nobody wants to do this, but I mean, technically you could do this. And works like this. It also has a mode similar to application-assisted sharding, where it is the client that connects directly to the shards, to the workers to perform the magic. But it's only for Java applications. It's a specially crafted Java driver, so that your application doesn't need to implement the logic. The driver implements the logic for you. Yeah, it becomes more complicated because it supports some high availability components here to support multiple coordinators, which require, for them to support this functionality, something called DCS, a Distributed Consensus Store, which is another small database like etcd, console, zookeeper. And the coordinators talk to this DCS, which is 3 nodes. This is 3 nodes, okay, for high availability purposes, for consensus. Okay, so now we need to deploy these servers. So all the, you get the thing, right? We need the replicas to configure Postgres here with all the configuration details, to configure Sharding Sphere with all the configuration details, with configure Zookeeper cluster with all the configuration details. So again, my point is this is damn hard. So I'll do a quick demo, but before moving to that, some questions about this?
Perguntar em português, o Citus ele lida com a disponibilidade nativamente, pelo que eu entendi. Mas o FDW não, né? Teria que ter algum programático fora para gerenciar com aquele arquivo.
Citus handles the HA automatically or need to do this manual intervention?
It's separate from Citus. So you need to build your own HA components.
And then the second part of the question is, when you do the FTW plus partitioning, you need to handle the HA.
Also the same. Yeah.
Same problem, right?
Yeah. Same problem. Same problem. I would say same solution.
Perguntas?
How you can do a backup routing in the main?
That's a very interesting question. How do we do backups? Because now we have multiple databases. Well, there's 2 options. First, I can take inconsistent backups. Okay? Don't run away yet. Right? I can just do a backup here, and that's it, right? If I start them more or less at the same time. Now, this is only okay if your application can handle this kind of inconsistencies in data. And actually, some applications do. And I said, when you go sharding, you need to take some caveats to accept some drawbacks. Sometimes it is that you need to deal with some inconsistent data model. If your data can reconcile this, it's okay. Most cases are not, but some are. So actually, some sharding solutions do not have something like a consistent distributed backup. But Citus does. And it's not difficult to implement, so also for partitioning, you can do the same. And the key is that you run a distributed transaction. In Postgres, for example, there's 2PC, two-phase commit, which is a way of running a distributed transaction, where you insert a mark of when a distributed backup will start. And before doing this, you start the backups on all the nodes. And then when you restore, you say restore to this point exactly in time. And then you restore to a consistent point from a distributed perspective. Citus has this implemented, and I'm already going to show what the demo is, but we have also implemented for partitioning with FDWs, the same technique. It's quite simple, actually. Okay, let me show the demo. That's one thing that will take a few minutes to run, and I'll take some more questions. The demo, I'm not going to run everything now, because I guess I don't have much time anymore. Okay, so for this demo, I'm going to use a software that we have built for running, orchestrating Postgres, which is called StackGres. It's fully open source and runs on Kubernetes. Okay, I'm not going to talk about more. I just want to show you the demo. One of the goals is to make something like complexity of creating a cluster that you have seen now how complex it is, as simple as this. For example, using Citus. This is it. Write this YAML, and you'll get a cluster with one coordinator. For example, in this case, we don't have HA. OK, you want HA? Let's write a number 2 here. Super difficult, right? With 3 shards, each shard with 2 instances, which means it has high availability, each shard. So this configuration will create 7 Postgres nodes. 1 for the coordinator and 6 for the shards, each one with 10 gigabytes of disk, and sharding technology Citus. That's it. It's really hard, right? How do you execute this? I already ran this, but you basically do, if you have a Kubernetes cluster configured, you say apply -f this, and that's it. And a few minutes later, all right, right now I'm using a Kubernetes technology that is actually quite slow to create resources, but that's why I did for you already this, and this is what you get. This is the web UI, and here in the bottom part, you can see all the nodes. So this creates the coordinator 0, and then shard 0 does 0, the 0 does 1, which is the replica, et cetera, et cetera. So you see all the clusters created here with all the capacities. And this is a fully working cluster. I didn't do anything else other than run this command. And I'm going to run this with another technology for you to see that I'm not lying. And from here, you just get Citus. So you can do something like, yes, for example, this. I can connect to the coordinator. Actually, better, let me show you this. This is what Patroni, the high availability component that is built into this software product, sees the whole cluster. And again, this command I can run, connection is not super fast, look like, after running this YAML file. And you can see here that, oh, there's a whole cluster distributed. All nodes are connected. There is the coordinator, there's the replicas, there's replication in between them. So there's high availability at all the levels except for the coordinator. I just chose a one there. I can fix this actually right now if you want. And it just works. I only need to type this YAML. Now, let's say I don't like Citus. I prefer to use foreign data wrappers and partitions. For example, because Citus is not compatible with timescale, but I can do timescale with partitions and foreign data wrappers. So if I want to have sharding with virtual shards with hypertables, which is another way of partitioning, 3 levels, I can use timescale on top of foreign data wrappers. So how we also wanted to support this technology with foreign data wrappers. And here's the example file that, by the way, I'm just going to run. Let me create this cluster. So you also see how long it will take. And I'll show you now the file. Let me open it here. That's probably already finished, right? Yes. So do you see a lot of difference? It's pretty much the same, right? The only difference is that type DDP. DDP is kind of distributed data partitioning. That's the name we came up for this technology in reality. Everything else is the same, super simple. How many coordinators do you want? How many replicas do you want? How many shards do you want? And this will create all the infrastructure for you. We'll create the 4 index wrappers across the servers, includes connection pooling, high availability, all built in into, and we will see now, it will create a cluster in a few minutes. And it comes with a lot of functions inside the Postgres database. It will create a database called DB, and this database contains functions that we inject already. In Citus, we inject Citus with functions. Here, we inject our own custom functions for doing this, which lets you create a distributed table, for example. You say, I want this table to be distributed by this column, the sharding criteria, and it will calculate all these ranges, with the build-to shards, all the math, and we'll create the tables, the partitions, everything for you. And last but not least, by the way, this is probably creating already, so if I do something like, yeah, you can see that the 4 index wrappers are creating here. It will be ready in some minutes. This I'm using a technology by Google Cloud, which creates servers on demand to run every workload. So first you need to create the server and then my capacity. But that's why it takes a little bit more. Normally this runs in less than 1 minute to create a cluster like this. Here it will take like 5. And last but not least, we also support sharding sphere. In this case, yeah, whatever. Let's open read-only. Slightly more involved, but not that much, the YAML file. And the only difference essentially is that the type is sharding sphere, and that I have to specify configuration that is specific to sharding sphere. Like for example, what type I want. It has a mode called standalone with a single coordinator, or a mode called cluster, which supports multiple coordinators. And the cluster mode requires you to specify also which distributed consensus data store you're going to use it, like etcd or zookeeper. So just imagine the complexity that all this does in this case in Kubernetes, creating all the components, wiring them up. This is essentially production quality. You just need to type what here, 27 lines of this super simple job. So summary and takeaway here is that I'll leave this while we get some questions. I'll show this creating for you to see that is creating. But our goal was to make sharding accessible to mere humans, because creating all this architecture for sharding is really, really complex. Takes a lot of time. Even just to do this automatically, right? It's a huge effort. It's typically weeks, months effort. And you can do now with a simple YAML. So that was one of our goals. Questions? Or more questions?
If I want to add a new workflow shard, who is responsible to move all the data to the new server?
Yeah, that's a very good question. It depends on the technology in this case. Well, first of all, we're trying to make this is a kind of a first step, right? And right now, we are just trying to target whatever technology supports us of today. So out of these 3 technologies, Citus explicitly supports rebalancing, resharding. So you don't need to do anything, just edit this YAML file, add another node, it will be created, and then you still have to run these commands, specifically on Citus, to call the resharding functions. Easy. With FDWs, there's no such functionality yet. We will develop it. You can use this with logical replication, Postgres logical replication. It's a bit involved, but can be done. So it will also be fully automated. And with sharding sphere, I believe there's some support, but it's not implemented here yet. But it'll get there.
How do you specify the sharding rule?
The sharding, sorry?
The sharding rules?
Yeah, the sharding criteria.
Yeah, criteria.
So in the first 2 cases, you specify by calling some function, some UDF, technically, user-defined function. So Citus provides some functions. For example, we may open another shell here. Let me see. Let's get to pSQL, for example. If we connect to the Citus one, for example, first, Citus.
Can you increase the font?
Yes, thank you. If I list the Citus extension, you will see that it comes with a lot of functions. And these functions are what allows me to create this. In particular, there's a function called create distributed table. Let's say like this. Here you have create distributed table. And basically, it takes a table name and the column or columns which are the sharding criteria. So you create a table with create table, and then you call create distributed table, and then the table argument and the column typically, or columns, and it will do everything for you behind the scenes. For the FDW, we have created a very similar function with a very similar name that does essentially the same.
Does it make sense to have a sharding criteria that's based on location?
Yes, it may make sense. That's why I said that sharding, you need to find the sharding. Finding the sharding criteria is an activity where you may be fairly spending a month on it, because you may want to analyze all your data and run some simulations. If I use this, how my data is going to be split across the shards. How easy is going to be shard rebalancing. And it's a very critical decision. All my queries, or most of my queries that I want them to target a single shard, can they all add the where clause that will include my sharding column? Because if my queries do not include this where sharding column equals a value, the coordinator will send the queries to all the nodes. So it's a critical part of it. And it's very custom to your application. So can be the geo? Yes, can be, perfectly. If your application is, if you're going to do queries restricted to one geography, then sounds like, yeah.
There's a challenge with schema changes, DDL.
Yes. Now DDL becomes more complicated, because now if I want to change the DDL, oh, there's a lot of places. Citus also comes with a DDL function for this. Apply shard DDL command, right? I think it's this one. There's a few functions that will run this on every server. On the other ones, there's still work to do. So Citus is, let's say, the more advanced one as of today, in Postgres land at least. But these kind of things, I mean, this is the easiest part. You can also script by yourself. It's not ideal, but you can do. In particular, in StackGres, we have a functionality called manage SQL, which is a script or set of scripts that you attach to the cluster definition. It will be part of this same YAML that we have seen. I don't have the example here, but it will be part of the, ooh, there's an error there, nice, of the same YAML file. And so there's a section here you can add that's manage SQL. And there you can add a script. And it's managed because if you edit the script and do kubectl apply, it will reapply it. And it will reapply it on every node. So this you can use already to do this. But yeah, it's a challenge.
A gente não tem muito tempo, eu tenho uma última perguntinha pra gente seguir aqui. Se nós vamos embora, o cara do estacionamento vai bater em mim. Alguma pergunta?
What if after running for some time, I realize that my sharding criteria is not ideal? Is that a way to change it?
No, I mean, it's bad. Not the end of the world. You will essentially need to create a parallel cluster with the new sharding criteria, and then use a mechanism to move all the data over. This will probably involve logical replication with really high volumes. So, I mean, it's doable. It will take a lot of effort to do.
Fechou? Bem, então tá, muito obrigado.
Thank you. Obrigado. Yes. Okay.